Talk about some technical things called weighted sums, dot products, and matrix products. Let's suppose we're going to hire someone. We're a company and we've got job candidates, and we've rated each of our applicants according to their technical skills and their soft skills. Each rating is on a scale from 1 to 5, for example. How will we decide who ranks the highest overall? We could decide that 70% of their final score will be based on their technical skills and 30% on their soft skills. Then for each applicant, we could compute their overall score being zero point 0.7 times their technical skills rating plus zero point 0.3 times their soft skills rating. This is called a weighted sum, and the zero point 0.7 and the zero point 0.3 are called the weights. It's not related to weights like pounds or kilograms or tons, though it's more like the importance of something. In this case, the size of the weight exactly tells us how important that category is. But that's not always the case in other situations when the things we're combining are in different units, like hours versus days or meters versus kilometers. It's often a good idea to rescale our predictors. A technical skills rating is like a predictor of how well they will do at that part of the job. We want to often rescale them so all the numbers are roughly in the same range, like everything is between 0 and 1, or things have a mean of 0 and a standard deviation of 1. A lot of AI does that automatically. We can talk more about that some other day. Weighted sums are related to a weighted average, but here we aren't dividing by anything like we usually do for an average. The weights here, 70% and 30%, add up to 1.0 or 100%, but weights don't always have to add up to 100%, and in most cases in AI computations, they don't. We could even have some negative weights. For example, we could have a third category for our job candidates, along with tech skills and soft skills, called did they get bad references? And the higher the rating on that, the lower we would rate that candidate overall. So we would give that a negative weight. So it's perfectly fine to have negative weights. In a previous video called Module 40E, More Predictors, Cancer Dataset, we talked about computing a score or a logit value by doing something like negative 0.0015 times the area of cells in a microscope image, plus 1 times the compactness of the cells in the microscope image. Or more generally, we could say like some number called M1, M kind of being like slope, times predictor 1 plus M2 times predictor 2 plus et cetera if you have more predictors. In this context, we decide or let the computer decide what values to use, like the negative 0.0015 or M1 to get the best possible predictions. I said we used M because these values were kind of like slope, like y equals mx plus b, but we could call them W1, W2, et cetera, for weight 1, weight 2, et cetera. We can rewrite a weighted sum by making a list of the weights and a list of the predictors or the things that we are weighting. So we could take 0.7 times technical skills rating plus 0.3 times soft skills rating and turn that into two lists, one of them being 0.7 comma 0.3 for the weights and tech skills rating comma soft skills rating for the predictors. We can call those two lists of numbers each a vector. There's a common math thing that we can do that takes two vectors and computes the weighted sum from them. It involves multiplying, so it's called a product. And we write it with a dot, so it's called the dot product of the vectors. So we'd say 0.7, 0.3 as a vector, dot, technical skills rating, comma, soft skills rating as a vector. And that just gives us 0.7 times tech skills rating plus 0.3 times soft skills rating as before. In spreadsheets, this dot product idea is called sum product because we're computing the products for each pair and then we're summing those products. If the predictors for a candidate are large in the same places that the weights are large, we'll get a very large result compared to other possible results. So if we had a candidate whose tech skills was 5 and soft skills was 1, 0.7 comma 0.3 dot 0.5 dot 5 comma 1 gives 0.7 times 5 plus 0.3 times 1, which is 3.5 plus 0.3 or 3.8. So that's not a bad overall score. This would mean that the job candidate is well aligned with our skill priorities. But if the predictor for tech skills for a candidate is small, even though the weight is large on tech skills, and the predictor for soft skills is large, even though the weight is small, then we won't get a large result at all. So if we had a candidate with a score of 1 for tech skills and 5 for soft skills, we would get 0.7 times 1 plus 0.3 times 5, which gives us 0.7 plus 1.5 or 2.2, not very large. So this candidate is not well aligned with our skill priorities, but it's kind of going in a different direction, but not exactly opposite. It's more like north versus east rather than north versus south. So the dot product can tell you the extent to which two vectors are well aligned. What if we have a pool of candidates, but we have a few different jobs that we're hiring for? Maybe some engineers, some tech support, some salespeople, um, uh, job openings. We might have a different set of weights to compute the overall score related to an engineering job than for a sales job. Like this, we might have engineering would have weights of 0.8, comma 0.2. Tech support might have weights of 0.55 and 0.45. Sales might have weights of 0.1 and 0.9. We could keep these each in their own separate list, or we can make a table of them, which we could call a matrix like this. So reading across the rows, 0.8, 0.2, next row, 0.55, 0.45, next row, 0.1, 0.9. So that would be a 3-row, 2-column matrix. Suppose we have a candidate whose ratings are tech skills of 2, soft skills of 4. We can compute their overall score for each job by doing the dot product of each row of the matrix with the vector of the candidate's ratings. We call this the matrix vector product. And in math notation, we would write it as this 3-row, 2-column vector matrix times the column vector 2 above a 2 and then 4. And then this shows the computation of 0.8 times 0.2 times 0.8 times 2 plus 0.2 times 4 gives us 2.4. Next row, 0.55 times 2 plus 0.45 times 4 equals 2.9. 0.1 times 2 plus 0.9 times 4 gives us 3.8. So this candidate gets a 2.4 rating for the engineering job, a 2.9 rating for the tech support job, and a 3.8 rating for the sales job. It seems strange at first that we wrote the candidate scores in a column format rather than a row format. You can learn more about this idea in a linear algebra class like EMU's Math 122, but for now, don't worry about it. Doing a matrix vector product is also called a linear transformation. Large language models do this sort of thing when processing vectors that relate to words. The matrix represents the things that the LLM has learned, and they don't change as we go through the process of rating a candidate or whatever. And the vector is a word or a token that we're processing, and we'll see more about that in the next video. It's fun and often useful to make connections between various areas in STEM. In a statistics class, a textbook might show the formula for the correlation coefficient between two variables as R equals this big fraction. The sigma here, this E-looking thing, means to take the sum of. And so the numerator is summing the products of the X deviations from the mean of X with the Y deviations from the mean of Y, which is the same as computing the dot product of those deviations. So dot products are highly related to the correlation between things, which can be positive or negative, kind of like we were talking about alignment of a job candidate with the ratings. The denominator here isn't a dot product, it's just a rescaling of the result of the dot product, so we won't worry about it here. Don't worry if you've never seen this formula before or you saw it and didn't understand it before. I won't be quizzing you on it, but it is nice to know that dot products are related to correlations.